So I thought I'd quickly go over some things again to recap. We have a sound source like a speaker in the middle here, and it's blasting out. And say if this was a 100-watt power source, sound power source, it's exactly like a light bulb. It's blasting out sound into the room in a way that a light bulb does, but the sound power doesn't actually change. The sound power is, look, there's a 100-watt power source. In the same way, wherever I stand in the room, it's still a 100-watt light bulb. It's quite an important concept to grasp. What we're actually measuring is, say we're somewhere in the room over here where I'm drawing the dark, we're going to either get sound intensity or light intensity, depending on which one we were talking about. Sound intensity, what do we actually mean by sound intensity? Well, let's call that I for sound intensity. It actually equals to the amount of power or joules per second that is traveling through a particular area at per second, how many joules per second is traveling through this area. Now, if we make this 1 meter by 1 meter, what we have is joules per second, or watts power per meter squared. So intensity is the watts per meter squared. Brilliant. So that is what sound intensity is defined by. But what is the scale and what are the units? Well, let's have a look at this, because let's have a look at the human scale of it. So what is the smallest and the largest intensity that we can hear? Right. Well, the smallest intensity is absolutely incredible. It's what we're going to call 0 dB, but let's not get ahead of ourselves. If we say intensity 0 is actually 1 trillionth of a watt per square meter. That's the equivalent of being able to hear 1 watt of energy smeared over 3 times the surface area of Germany. That energy moves your eardrum 1/6 of the diameter of a hydrogen atom. It's insane how brilliant your hearing is at that level. It's absolutely incredible. In fact, if it went any lower, you'd be able to hear the movement of air molecules. So it's almost as low as it could possibly be. So that's the intensity. I0 is 1 trillionth. And let's write that. That is a naught with 12 decimal places over in this direction. That is 1 trillionth. Now, I've moved the decimal point 12 places backwards. So the easiest way of writing that is 10 to the minus 12. Now, it's worth noting what these engineering terms are. This 10 to the minus 12 is actually really, really cool way of working stuff out. So, for example, you know what 10 squared is 10 times 10, so that's 100. You'll notice that the same amount of noughts as the exponential 2. Absolutely the same thing if we go up an order of magnitude, i.e. increasing the exponential by another 1, is we get 1,000, 10 times 10 times 10. 10 times 4 equals, with 4 zeros on the end. It's just so easy. Right, so we can go the opposite direction as well. So 10 to the minus 1 equals 0.1. Now, one that's very, very useful to know is 10 to the 0 equals 1. 10 to the 1 equals 10. Right, so we've kind of grasped what these exponentials are. Now, what is the most intense sound that you would like to hear? Well, let's just choose a sound that starts to make our ears really uncomfortable and actually hurt. So this is going to be IH, where it hurts. That is actually roughly 1 watt per square meter. 1 watt per square meter. Or you could write that another way, 10 to the 0 watts per square meter. So we have a scale that is 1 trillion big. It's absolutely huge. And that's actually a bit unmanageable. Not only that, the way that the human ear perceives sound means that you have to get things 10 times as intense to hear it being twice as loud or thereabouts, depending on the frequency. But roughly speaking, if something's 10 times louder, it feels about twice as loud. So it would be neat if we shifted the scale so it went up in 10 times increments. So we're starting here at 10 to the minus 12, and we're finishing here at 10 to the naught. So we have 10 to the minus 11, we have 10 to the minus 10, we've got 10 to the minus 9, and we're just going to go all the way up to this 10 to the minus naught. So 10 to the minus 1 will be there, and we go up like that. Now, that's really cool because it's each of these increments is 10 times louder, so each of these increments feels like it's twice as intense as before. So we're trying to, this scale is a lot easier. You can see this scale is already easier to deal with as long as we remain as exponentials of 10. What would be even better if we managed to make this scale so it went 0, 1, 2, 3, all the way up to this last number, which will be 12, of course, because we've got from minus 12 to 0, we've got 12 increments up there. So going all the way up to there to 12. 0 to 12 would be really handy. So if a sound is at this lowest intensity, it would be 0 dB, or 0 bell in actual fact, but we'll get onto that in a second. We're getting ahead of ourselves again. So the intensity at its lowest intensity is 0, and when it hurts, it's at 12. Well, how do we do that? Well, there's a brilliant thing called the logarithm. Now, logarithm base 10 of, say, a number x, what that's actually saying is like the opposite of raising 10 to a power. So you're saying this whole term means what number do we have to raise 10 by to get this number, and that will give us our answer. So say if x was 1,000, what number do we have to raise 10 by to get 1,000? Well, I've got it here actually. 10 to the 3 is 1,000. So the answer to that would be 3. Well, that is cool because look, 10 to the minus 9 we want to 10 to the minus 9 we want to make 3. So how do we do this? So what we're going to do is write down the equation for the bell. This is the bell, and this is log base 10 of the thing that you're trying to measure, the intensity that you're measuring, over this reference intensity, which we're going to make this I0, which we originally talked about, this 10 to the 1 trillionth of a watt meter squared, because that's the lowest we can hit. So that's going to be our reference value. Well, let's have a look at this minus 9. We wanted to make it 3, didn't we? Have we achieved that? Well, let's have a look. If we put the numbers in, we can replace that by 10 to the minus 9 over 10 to the minus 12. And the other great thing about exponentials is they're really, really easy to work with, because the difference between this and this is 3, so I can cancel that out and then make this minus 3, right? 10 over 10 to the minus 3 is exactly the same as 10 to the 3. Right, what number do we have to raise 10 by to get 10 to the 3? Well, hopefully that's really obvious. It's 3. So, brilliantly, we've done it. We've managed to make this scale 0, 1, 2, 3 up to 12, because essentially logarithms are the opposite of exponentials. So that is a masterstroke there. So we have a scale that goes from 0 to 12 at the moment. However, that's actually a little bit too small. So what we're actually going to do is introduce the decibel, which is actually 10 log base 10 of your intensity measured over the intensity 0. Now, in this case, if it was 10 to the minus thing, it would be 10 times 3, so it would now be 30. So the scale now is going from 0 all the way up to 120. And that's a really useful scale. you'll notice 120 decibels is where your ears start to really hurt, and 0 decibels is the scale where it's really just about on the perception of hearing. And it has to be very special conditions for you to be able to hear that, by the way. So here's some really interesting ones. If you had a ratio in here that was 2, i.e. a sound that was twice as loud as the one before, that actually, if you put 2 into your calculator and put and do a logarithm of 2 and multiply it by 10, you actually get 3 dB. Now 3 dB means that the sound intensity is twice, you've increased the sound intensity by twice, or minus 3 dB, you would have halved the sound intensity. So that's a really useful number to know, as is 10 dB. 1 dB in the original Bell scale, we know was multiplying it by 10. 10 dB, because it's the deciscale, is also 10 times. So 10 dB equals 10 times 3 dB equals 2 times. They're very useful ones to know. So that is in sound intensity and why we convert it into the decibel scale. So just remember this 10 log 10 and the intensity measured over the intensity reference. Thank you.